Chapter 8 is dealing with potential energy, kinetic energy, and conservation of energy. And we're first going to talk about conservative and non-conservative forces. Conservative force is when work is stored in a form that you can use later. Examples would be like gravity. A non-conservative force means it's pretty much wasted. The energy goes somewhere and we can't use it later. For example, friction. Work done by conservative forces moving around an object in a closed path is zero, meaning there is no work done. And here it shows you a picture that the work done by a conservative force is zero. When we talk about energy, one of the main ways that we have energy is potential energy. This is energy that's stored. The book uses the symbol U, so in a lot of the pictures they'll have a U. I use PE, standing for potential energy. And there's different types of potential energy that we're going to look at. One is gravitational potential energy, and I use GPE to stand for gravitational potential energy. And the formula to calculate gravitational potential energy is M times G times H, or in other words, mass times acceleration due to gravity times height. And mass would be in kilograms, and G is our 9.8 meters per second squared, and height would have to be in meters. And when I multiply all those units together, I get the energy unit, which is joules. And for elastic potential energy, like what you would have in a spring, we had this in chapter 7, and I use EPE for elastic potential energy. It's 1/2 kx squared, where k is your spring constant, and x is the amount that it's stretched from equilibrium. And once again, all energy is going to be labeled in joules. When you're looking at problems that you're going to be doing in your assignment, these two equations, those are going to be used in 8.2. Also going to be looking at that in 8.10 and 8.14. Specifically, this one is used in 8.14, and these two problems both use this first equation. Now, mechanical energy is the total amount of energy that you're going to have in your system, and that means that it's going to be the potential energy plus your kinetic energy. And as long as your energy is conserved, that means the amount of energy that you have at the end has to be the same as that you have at the beginning, which means the total amount of energy stays constant. Conservation of energy makes a lot of our mechanical problems that we've been using, our kinematics problems, a lot easier. For example, if we start out here and we have some keys, then we know that their potential energy is mgh, and right now they're not moving, so their kinetic energy is zero. By the time they get down to the bottom, that means their potential energy has gone to zero because they don't have a height anymore, and it's all converted into kinetic energy. So that means that the potential energy that they had at the beginning would be equal to the kinetic that they had at the end. So like I said, if energy is conserved, the final energy is equal to the initial, or in other words, the kinetic energy plus the potential energy at the beginning, or the end, is going to be equal to the kinetic energy plus the potential energy at the beginning. In a lot of cases, for example, in the case of the keys in the last problem, we had gravitational potential energy to start with, and we ended up with kinetic energy. So that means your mgh at the beginning would be equal to the 1/2 mv squared at the end. And one thing that you'll probably see in some problems is, since I have an m on both sides, that m could be canceled out, which means they might not even give you the mass. G is your 9.8, they could give you a height, and they could ask you for the velocity later. Or vice versa, they could give you the velocity and ask you to find the height later, because there's only two variables, the velocity and the height, because G is a constant and your m's can cancel out. And you're going to see a lot of problems on your assignment that are going to deal with this conservation of energy concept. For example, 8.22, 8.24, 8.6. Those are all dealing with that. And this equation that we used where we have the beginning and the end like that, where the ends can cancel out, there's a problem called sliding in socks. And sliding in socks, you're going to be using this whole thing. These other problems, you're going to be dealing with the concepts of conservation of energy. And also, before I forget, 8.32 and 8.64 deal with this idea that mechanical energy is the potential plus the kinetic. Work that's done by non-conservative forces. These would be things like friction or any kind of air resistance, which is also friction. And if we want to find out the work that's done by non-conservative forces, that's going to be equal to your change in mechanical energy. So you could find the mechanical energy at the beginning, and we would take ME final, so mechanical energy at the end minus the mechanical energy at the beginning, and that would be equal to your work. And remember, your mechanical energy is your kinetic and your potential. So this would be your total energy at the end, your total energy at the beginning. So like KE plus PE at the end, and then subtract the KE plus the PE at the beginning. We know if energy is conserved, those two are equal. If they're not equal, then that means that work was done and it's non-conservative forces. And this you would be using in problem 8.40. Now, potential energy curves and equipotentials, we can look at a plot of gravitational potential energy. So in this case, they're showing us our height. So right here we would have potential energy, and this would be at a maximum. And also over here you would have a lot of potential energy. So when the ball was here and here, it would have the same amount of potential energy. As we get down here, we can see that this potential energy is very small. Here the potential energy is bigger, and here the potential energy is a lot bigger. But what's interesting to note is K is our kinetic energy. So when our potential energy is at a low, our kinetic energy is at a high. And here it looks like you have about equal amounts, and then at the top you're going to have lots of potential energy but very little kinetic. And there is one of the problems that you have where it asks you to rank the speed at different locations. The speed is going to be based on the height. So if you have a small height, like in this case where it's very low to the ground, if you have a small height, that means you're going to have a lot of kinetic energy. And anywhere where they have the same height, they're going to have the same amount of potential energy, which means they would have the same amount of kinetic energy. And here, where it's going to be going the fastest, is where your potential energy is at a minimum. And like I said, there is one of those plots of gravitational potential energy that you have to look at. And I think, I'm not sure what question, but it might be one that's just called conservation of energy. For a spring, we kind of have the same kind of concept, except now we're looking at that 1/2 kx squared. So here, if we're looking at our potential energy, we're going to have lots of potential energy. You can see it's the 1/2 k. They call it a squared, standing for amplitude. But you're going to have a maximum at those two places where your potential energy here is going to be 0. And if you would think about a pendulum or anything else, whenever you're passing this equilibrium point, that's when it's going to be moving the fastest. So you have your pendulum that goes up, then it's going to speed up, reach a maximum speed here, and then slow down on the other side. And your potential energy is going to be the greatest at the ends, and it's going to be the smallest here, which means if the potential energy is the smallest at the bottom, then the kinetic energy is going to be the largest. Contour maps are also forms of potential energy curves, meaning greatest potential energy here, smallest potential energy here, and it's based on the heights. And in Chapter 8, the summary talks about conservative forces conserving mechanical energy, where non-conservative forces do not. Conservative forces don't do any work, and work done by a conservative force is independent of the path, meaning it doesn't matter what way it gets there. Conservative forces would be things like gravity and springs. Non-conservative forces would be friction and air resistance. We talked about that energy in the form of potential and kinetic can be transferred back and forth, and that if we have work done by a conservative force, it's the same as the change in your energy. And we had gravitational potential energy, which was mgh, and for your spring it is 1/2 kx squared. And mechanical energy is the sum of the kinetic and potential. And if we have any work done by non-conservative forces, that's equal to the change in mechanical energy. And then finally we looked at those potential energy curves. And that will finish up chapter 8.